If you have ever opened a bottle of isopropyl alcohol and instantly recognized that strong, sharp smell, it might be hard to imagine that the clear liquid in your hand began its life inside a refinery, surrounded by pipes, reactors, and chemical equipment. It seems like such a simple household product, almost too simple to require much effort. But the actual journey from raw materials to the bottle in your medicine cabinet is filled with controlled reactions, large machines, and several layers of purification. What looks ordinary is actually the final result of an industrial chain that involves petroleum chemistry, high temperatures, carefully measured pressures, and a lot of safety protocols. The product seems straightforward, but everything behind it is anything but. The process begins with crude oil and natural gas, which are the sources of a key component called propylene. When crude oil is heated inside a refinery, it separates into different materials based on their boiling points. Heavy substances settle at the bottom, medium fuels remain in the middle, and very light gases rise to the top of the distillation column. Among these gases is propylene. Refineries separate the propylene, cool it down, remove other gases mixed with it, and store it in pressurized tanks. This purified propylene gas becomes the main ingredient needed to make isopropyl alcohol. Without the refining step, there would be no way to obtain enough propylene to support global demand for IPA, which is used everywhere from hospitals to electronics factories. Even though propylene is the main ingredient, the other ingredient, water, is just as important. Factories cannot use untreated water because even small impurities can interfere with the chemistry. Minerals, metal ions, and dissolved salts can disrupt the reaction or create unwanted byproducts. So before the water is used, it goes through a purification process. Some plants use reverse osmosis systems, others use deionization tanks, and some use multi-stage filtration. The objective is to strip the water of any contaminants that could affect the reaction later. Only after both ingredients are refined and ready does the real transformation begin. Most modern plants rely on something called direct hydration. In this method, propylene gas and steam are fed into a reactor, operating under carefully controlled temperature and pressure conditions. Inside the reactor is a solid catalyst, usually phosphoric acid attached to a support material. The job of the catalyst is to help the reaction take place quickly without being consumed by it. Propylene on its own does not react easily with water at normal conditions. However, when heated, pressurized, and exposed to the catalyst, the molecules begin to interact. The propylene combines with water molecules and forms crude isopropyl alcohol. A number of sensors monitor the reactor constantly. If the temperature strays from the desired range, the reaction may slow down or produce unwanted compounds. If the pressure drops too low, the conversion efficiency decreases. If it rises too high, equipment could be damaged. Operators keep a close eye on every parameter, adjusting feed rates when needed. When the reaction is finished, the mixture that leaves the reactor is not pure isopropyl alcohol. It is a combination of water, newly formed alcohol, unreacted propylene, and trace byproducts. Instead of wasting any of the unreacted propylene, the factory captures it and sends it back into the system to be used again. This recycling improves efficiency and reduces overall cost. The remaining liquid flows into purification units, which are critical to producing usable IPA. Without purification, the mixture would be far too contaminated to be used for cleaning, disinfecting, or industrial work. The main purification method is distillation. Distillation towers are tall structures filled with trays or packing materials that help separate liquids based on their boiling points. Because isopropyl alcohol boils at a lower temperature than water, it evaporates more easily. Inside the tower, heat rises from below and cooler vapor descends from above. As the mixture interacts with the trays, the alcohol vapor becomes cleaner and cleaner the higher it climbs. By the time it reaches the top of the tower, it is mostly purified IPA vapor. That vapor condenses into liquid once cooled. But even after this step, the mixture is still not pure enough for medical or industrial use. The challenge comes from the fact that water and isopropyl alcohol forms something known as an azeotrope. An azeotrope is a mixture that behaves like a single substance when boiled. It means you cannot separate the components completely using regular distillation because they evaporate at the same ratio. To solve this, factories use advanced purification methods. One technique is pressure swing distillation, which changes pressure levels to break the azeotrope. Another method uses materials called molecular sieves, which have tiny pores that trap water molecules while allowing alcohol molecules to pass through. These additional steps bring the purity of the alcohol to very high levels, often above 99%, which is essential for many applications. Once the alcohol is purified, it is moved into large stainless steel tanks. Even this storage step requires careful planning. Isopropyl alcohol evaporates quickly and produces flammable vapors that can ignite if exposed to sparks or flames. Therefore, factories use explosion-proof lights, anti-static flooring, ventilation systems, and grounding wires to prevent accidents. Any tank holding alcohol is sealed to prevent evaporation and is inspected regularly for leaks. Sensors placed around the storage area continuously check vapor levels to ensure everything remains safe. In many facilities, strict rules prohibit open flames, smoking, or even certain electrical tools anywhere near the storage area. After storage, the alcohol may be sold at its high purity level or blended into specific concentrations. One of the most common household concentrations is 70%. While it might seem counterintuitive, 70% is more effective at disinfecting surfaces than pure alcohol. The water in the mixture slows the evaporation rate, giving the alcohol more time to penetrate microorganisms. In blending tanks, operators mix high-purity IPA with precisely measured amounts of purified water. Mixing paddles rotate through the tank to ensure the solution is uniform. Instruments constantly check the alcohol concentration, and adjustments are made until the mixture is perfect. When blending is complete, the IPA is filtered again to remove any remaining particles or impurities. Filtration is especially crucial when producing alcohol for the electronics industry. Circuit boards, chips, and sensors are extremely sensitive to contamination, and even microscopic dust could interfere with their function. Electronic-grade IPA undergoes the most rigorous purification and filtration steps to ensure it leaves no residue behind. Once purified and blended, the alcohol moves to the bottling stage. Automated machines clean and prepare empty bottles. The filling nozzles dispense precise amounts of IPA into each container. Conveyor belts move the bottles along to capping stations, where caps or spray tops are attached securely. The next step applies tamper-evident seals, ensuring consumers know the bottle has not been opened. Finally, labels are added, showing concentration, safety warnings, and batch codes. These batch codes link the bottle to all the data recorded during production, including test results, equipment logs, and worker inspections. Before the alcohol can leave the plant, it must pass a series of laboratory tests. Technicians analyze samples to check purity, concentration, pH level, color, density, and evaporation rate. They also test for impurities such as methanol or acetone, which must not exceed strict limits. If the batch fails any test, it is returned for reprocessing rather than being shipped out. Companies that supply hospitals or pharmaceutical facilities must maintain even stricter quality standards, and their products are tested thoroughly before approval. Once the IPA passes inspection, it is ready for distribution. It may be sent to pharmacies, hospitals, factories, laboratories, cleaning supply warehouses, or electronics facilities. Different industries use IPA in different ways. In hospitals, it disinfects equipment and prepares skin for injections. In homes, it wipes away smudges, removes gum residue, cleans earphones, and disinfects surfaces. In factories, it removes oils from machinery, helps prepare surfaces for painting, and dissolves adhesives. In electronics production, it cleans circuit boards and delicate components without leaving damaging residue. Its versatility is one of the reasons factories produce millions of liters of IPA every year. Behind the scenes, chemical plants constantly look for ways to improve sustainability. Many facilities recycle water used in cooling and cleaning. They capture unreacted gases and reuse them. Distillation columns are insulated to reduce heat loss, and waste heat is often used to warm incoming streams of liquid. Some plants use renewable energy sources to power parts of the operation. Safety systems have also become more advanced, using sensors, automated shutdown systems, and computer controls to prevent accidents. Transporting IPA is another step that requires care. Tanker trucks carrying IPA must be grounded during loading and unloading too. Prevent sparks. Drivers follow strict transportation guidelines, and hazardous material rules determine which routes they can take. Warehouses store IPA in well-ventilated areas away from incompatible chemicals. Workers handling large containers receive specialized training. Every stage, from the refinery to the pharmacy shelf, includes safety measures designed to protect workers and consumers. The story of isopropyl alcohol might sound technical, but every step serves a purpose. It starts as a gas separated from crude oil, then makes its way through reactors, distillation columns, purification units, blending stations, bottling lines, and laboratory tests. Every part of the journey transforms it a little more until it becomes something people use every day. The next time you dab rubbing alcohol on a scraped knee, wipe a phone screen, or clean a countertop, remember that the clear liquid didn't appear out of nowhere. It is the result of chemistry, engineering, and careful production methods working together behind the scenes. What looks like a simple disinfectant is actually a product shaped by some of the most important technologies that keep modern life running smoothly.